Hi, my name is Liam Richardson. I'm doing this presentation with Dave Kubilka's Astronomy Fall 2018 course at Central Lakes College, Brainerd Lakes, Minnesota. I'm going to be covering three topics of the five presented. My companion, Torin, will be covering the other two on his own in a separate video. So, one of the things that I'm going to be discussing is, as the title would suggest, we're talking about surface temperature of the Earth. The first topic that I'm talking about is how do we measure temperature using light? Well, we do this using infrared, and an infrared thermometer measures temperature by detecting the infrared energy emitted by all materials which are at temperatures above absolute zero. So this means that essentially anything on our planet is going to give off an infrared signature. This means that we can, with the right equipment, look at its temperature simply using the light without directly touching or being in close proximity with an object. Most basic design uses a lens to focus the infrared energy onto a detector, which converts the energy to an electrical signal that can be displayed in units of temperature after being compensated for ambient temperature variation. So basically what this means is the technology is going to do all the work for you. You just need to know how to operate it and understand that the infrared is how we measure the stuff. Now here's a little diagram. May not be helpful for us, but we can see that infrared radiation is part of the electromagnetic spectrum and occupies frequencies between visible light and radio waves. Within this waveband, only frequencies of about 0.7 microns to 20 microns are used for practical, everyday temperature measurements. This is because infrared detectors currently available to the industry are not sensitive enough to detect the very small amounts of energy available at wavelengths beyond 20 microns. As far as I know, this is going to be fairly relevant to us, but it's some useful information that we can apply should the situation arise. A couple examples of infrared thermometers that are handheld. In the top left here, we have a diagram showing that there's a varying degree of the measurement distance and the spot size that you can measure with. As you can see on the right hand side here, we have what appears to be a pretty typical infrared scanner displaying the temperature. So it appears fairly simple to use. I've never used one myself, but we can gather that they are quite simple to use. Here's an image of an infrared camera, essentially the same principle as the other infrared thermometer, except already projected onto an image. So the next topic that I'm going to be talking about is how do we identify dry ground, wet ground, and recent rainfall with surface temperature. So we've already learned how to measure the surface temperature, but now we need to figure out the conditions of the ground. So wet ground depletes the heating power of solar radiation because some energy goes into evaporating water instead of directly heating the ground. Basically, the way you can think about this is there's already a barrier for water between the ground and the rays of the sun, and the sun has to heat those up first before it can directly heat the ground. And that's where the energy transfer comes off, is the energy is put into evaporating that moisture. Lower air temperatures, such as a swath of wet land, are a direct result of some of the sun's energy being spent on evaporation rather than heating the ground. So we can deduce from this information that if you are getting infrared scans from an area that you know has had a storm go through, maybe some certain clouds, and you're seeing lower temperatures there, you can easily tell that there has been rainfall or snow or something like that. So in this image, what we're seeing is the estimated rainfall of a short period of time. This was taken from a radar image. It's covering Oklahoma and Texas primarily. And in this next slide here, we see the actual temperatures that were displayed in the next following days. As you can see, there is a high correlation between the rainfall and the actual temperatures that are being displayed. So we can tell that we can use the temperature to see if there has been rainfall or precipitation of any sort, be that snow or hail or anything like that, by finding the lower temperatures. So next, we've got a little discussion on urban heat islands and basically how they're caused. So urban heat islands, if you're not really aware of what they are, urban heat islands are highly populated areas, usually metropolitan cities that emit a lot of heat, quite as the name would suggest. So on a sunny day with light winds, temperatures in any big city can be several degrees higher than surrounding rural areas as concrete and buildings absorb solar radiation. If you look at a weather forecast for Minnesota, you will see that temperatures in 50 Lakes or Cross Lake or Brainerd will be significantly less than temperatures in Minneapolis, especially in the summer. And speaking of summer, when the dew points are high, urban nights can be oppressive as water vapor absorbs large amounts of infrared radiation emitted by buildings and concrete. This absorption causes the water vapor to warm and radiate at higher temperatures, thereby slowing or essentially halting the nocturnal cooling in the city. So this basically means that the cities stay hotter for longer and don't cool down as effectively as other cities would. On the left here we have an image of Minneapolis, and the dark areas are the warmer spots and the light areas are indicating ice and snow. So as you can see, there's like highways and the actual city itself have much hotter temperatures than everywhere else, and this is because of the human activity and the infrared energy being absorbed by concrete. On the right we have an image of Atlanta displayed in what appears to be infrared. The lighter colors like yellow and green indicate hotter temperatures. So you can see that the areas that have more buildings and more traffic are significantly hotter than the areas that don't have the traffic or buildings. So basically, that's all I have for my part of this presentation. Go ahead and smash that like button, and please subscribe and click that bell to join my notification squad, and I'll see you next time.